Good afternoon to you all again. My name
Good
is,
afternoon.
yes,
Yes,
my
good
name is,
afternoon.
my name is Teacher Kemba Wasperan, and I'll take you through today's chemistry. It's the first lesson that we are going to have in our new year. Happy New Year! Okay. So today we shall look at organic chemistry as it is one of the okay. Let's all of us mute so that we have one class. Okay. So as we wait for other students to join us along the way, we shall be introducing our today's lesson, and other students will find us along the way. Hope we are together. So organic chemistry, as we have been covering it in senior 5, today specifically I will handle mechanisms, how to do some mechanisms depending on different types of reactions that we have in organic chemistry. As we shall find out that organic chemistry is one of the parts of chemistry where most of us, the learners, like attempting. Most of us like to attempt those numbers whenever we enter into a paper of chemistry, whether paper 1 or paper 2. And we need to get it in our hands so that whenever we go into a paper, we'll be able to answer the questions as they will be asked to us. So today's lesson majorly we shall have these objectives so that by the end of this lesson, out there, everyone who is there should be able to identify different organic reactions that we have in organic chemistry, as we have looked out some of them in our senior 5. I believe that by now you have some information about organic chemistry, and we looked at some of the organic reactions, but we shall find out that if you are not aware or if you are not able to identify which type of reaction is this equation or is this reaction coming from, you find learners having a challenge in identifying and drawing those mechanisms, as we are always asked to do the outlining of the mechanism. So we shall be able to identify different organic reactions, and we explain and describe how those reactions occur. If you identify a given reaction, then we should be able to identify and explain how those reactions occur. Then we shall specifically give some examples in each, and then we outline susceptible mechanisms in each of the reactions or in each of the equations that we shall be given as we continue with the lesson. Hopefully that we are all together. Are we together? So I will request some of us, before I even outline my reactions, I would request some of you out there to raise up their hands and they tell me organic reactions that they know, the organic reactions that you have come across throughout the whole year of senior 5. Now we are going to senior 6, and I believe that majority of you have already covered some of these reactions. So any person out can raise up and tell us some of the reactions that we have. You can unmute yourself. Gimei, you can tell us one of the reactions that we have in organic chemistry. Unmute yourself, please. Gimei, unmute.
Oxidation reaction.
Yes. Thank you. Any other person to tell us?
Welcome.
Whitney, unmute and tell us.
Elimination reaction.
Thank you. Elimination reaction. Any other reaction? Okay. So as you have said, we have oxidation reactions. Then we have elimination reactions, as Witten has told us. So some of the reactions that I have outlined here, we have these reactions. Before let me go back. Let me go back. So we have these reactions, as you can see. We have electrophilic addition reactions. Before we introduce these reactions, when we were doing introduction to organic chemistry in senior 5 first term, we were able to, they introduced us the new terms, the terms that we had in organic chemistry, and one of them we had electrophiles. So anyone can unmute and can raise up the hand and tell me what could be the electrophile. Anyone can tell me? Yeah, Elvis, unmute yourself. Elvis, unmute.
Yes.
Yes, please. Elvis, can you hear me?
Yes.
Okay, unmute. You
Yes.
can tell.
An electrophile is an electron-seeking species.
Yes, that is an electron-seeking species, or in our language that we understand, the electron deficient species, or the species which lacks electrons or which wants electrons. Thank you for that submission. Then we also have nucleophile. So any other person can tell us what could be the nucleophile? You can raise up your hand and tell us what is the nucleophile. You can tell me what could be the nucleophiles, or as we can continue, as Elvis has told us, the electrophile, that is an electron-seeking species, or the electron-deficient species. So the nucleophile, that is an electron-rich species. It may be a molecule with negatively charged electron. It may be a negatively charged molecule, or it may be a molecule with lone pairs of electrons, which it can donate to organic compounds, as we shall see different reactions, how they occur in different mechanisms and reactions. So one of the reactions of organic reactions that we have electrophilic addition reaction. Anyone to tell us the electrophilic addition reaction? You can raise up the hand and you tell us what you know about electrophilic addition reaction. Anybody? Okay. So for us to be able to identify or outline different mechanisms, as I will define a mechanism in layman's language or in a language that we understand, as the steps that a reaction undergo to take place. If there is a reaction between, maybe the simplest reaction I can remember is like a reaction between alcohols and sulfuric acid. For that reaction to occur, which steps does it take? Which steps does it use for that reaction to occur? That could be a simple introduction, a simple definition of a mechanism. So before we outline a mechanism, you need to understand which reaction is this, because one day they may ask you to describe, maybe they tell you to describe the chemical reaction between a certain species, and then they tell you to outline the mechanism. So you need to be you need to be able to identify that, oh, this reaction is an electrophilic addition reaction. Then from there you can understand how does this reaction occur, and then you will be able to outline that mechanism. So electrophilic addition reactions in belief, those are reactions. Let me. So electrophilic addition reactions, these are reactions in which an electrophile is added to an unsaturated organic compound to form saturated organic compounds. We shall find out that, as we have said, that an electrophile, that is an electron-rich species, most of them will be having a positive charge, or it is a carbocation or a molecule or an atom carrying a positive charge seeking for an electron. And so they will react with unsaturated organic compounds as we form saturated organic compounds. And the saturated organic compounds, from the introduction to organic chemistry, these are compounds which have triple or double bonds. So which have triple or double bonds, and we have examples of those compounds. For example, we have alkenes, then we have alkynes. So these organic compounds, they have double bonds. They have an extra bond which is added to them compared to those saturated compounds with single bonds. So for example, alkenes, they have they have a double bond, and among those two bonds, we have a pi bond, as I believe that you have heard about this. So that pi bond in alkenes or in alkynes, for it acts as the center of high electron density. And so it can easily attack those electrons and donate that electron to electrophiles, and finally we shall form carbocations, as we shall see among the mechanisms how they occur. So, as I said, that we outline a reaction whereby, for this case, our reaction is electrophilic addition reaction. And as I've said, it is that reaction where an electrophile is added to an unsaturated organic compound to form a saturated organic compound, or in simple term, a reaction between organic compounds with double or triple bonds to form organic compounds with single bonds. Those are saturated organic compounds, as we shall see about some of the examples of these mechanisms. So, what is not happening here? So we have said such reactions are undergone by alkenes and alkynes. As I have said, alkenes, those are organic compounds which have double bonds, and alkynes, those are organic compounds which have triple bonds. And among those two bonds that among the bonds that they have a pi bond. A pi bond added to them acts at the center of high electron density to form it acts as a center of high electron density, and it can donate electrons towards electrophiles, and an electrophile will be added to that organic compound and we form a saturated organic compound. For example, we have reactions of alkenes where we have halogenation, we have hydrogenation. Those reactions of alkenes, halogenation, that is addition of halogens where we have iodine, we have chlorine, we have bromine, being added to alkenes, and we shall form alkyl halides, or we can form dihalides, depending on which reaction are we taking place, are we carrying out. And then we shall find out that those reactions, for example, halogenation of alkenes, it can take place in presence of carbon tetrachloride or tetrachloromethane. It was methane, not ethane. And or it can take place in presence of water. So I just did those two mechanisms so that they guide us whenever we are asked, any question in NEB or in mock or any paper that you shall be doing throughout the year. Once you are given an alkene and you are given a reaction between an alkene and other species, then we should be able to remember that these are electrophilic addition reactions, and so I expect to add that electrophile towards that organic compound. And another thing I need to know, I need to remember that I have to remove that double bond and I form a single bond, because I said unsaturated compounds, those are the ones which have double bonds or triple bonds, and for saturated we have those which have single bonds. So whenever you are given a reaction for an alkene, whether it is in a ring, whether it is aliphatic, as long as you see a double bond, then you should be able to you should remember that, oh, these organic compounds undergo electrophilic addition reactions. Are we together up to that point? Are we together up to that point, friends? Someone can unmute. Okay. Thank you. We can continue. So I did my mechanisms here, and this reaction that I made, I hope or some of you or all of you should have looked at what UNEP last year brought. Did you look at them? This one asking about history, maybe there is another link that you should use, but this link specifically is for chemistry, so you can use the other link, I mean the other document that was given to us, and you look for the link for history. So I was saying that those who happen to look at UNEP 2024, actually by today, since you are now the candidates of this year, you are the ones to sit exams this year. So you should be able, or you should have finished looking at what have I done? Okay. Let's see what I have done. Lost my link. Okay, sorry for the interruption rather. So I was saying that those who happen to look at UNEB last year, the way that UNEB asked the questions, they didn't bring the direct questions that majority of the students expected. But of course, the format remains the same. So the question they asked was kind of different from the questions which have always appeared in past papers. Who is this? Please, I will allow you to unmute later. So we had this reaction. It was a part B, and they wanted us to describe, because they said describe the reaction between 2-methylpropene with bromine in presence of, let me see. But the other one was in the presence of carbon tetrachloride. And so if you are asked such a question, you shouldn't panic, or you think that maybe the question is hard, but the question was not hard, because it was the real equation, the real equations or the real mechanisms that you guys have always been doing. But only that they changed the language and they said, describe the reaction. Majority of us, we are used to these questions where they tell us that complete the following equations and outline a susceptible mechanism. But for this case, they wanted us to describe the reaction. So if they tell you to describe the reaction, one, you should be able to identify which type of reaction is this reaction. If for example, I'm having 2-methylpropene and bromine, then you ask yourself, which type of reaction does this species undergo? So as I have told you above, that we are looking at electrophilic substitution reactions, where we have alkenes are reacting with electrophiles, forming saturated organic compounds. So for this case, I first tell the examiner that 2-methylpropene reacts with bromine in presence of carbon tetrachloride to form 2-bromo, 2-methyl. No, we form 2-methyl, 2-bromo. Let me see. We form 2-methyl 2-bromo. It is 2-methyl 2,1,2-dibromo propane. You first identify the reaction, which is electrophilic addition reaction. Then you talk about the product. You name the product which will be formed. Then in case sometimes one day they will now they don't give you the reagents. They can say describe the reaction of bromine with 2-methylpropene, and then they stop there and they say outline a mechanism. So for that case, you specify which condition are you outlining that mechanism in. If you are using in presence of carbon tetrachloride, then you say 2-methylpropene react with bromine in presence of carbon tetrachloride or tetrachloromethane to form, you name the product. For this product, it is 2-methyl-1,2-dibromo-propane as the final product. Then you outline the mechanism. So as I said that they undergo electrophilic addition reactions in presence of carbon tetrachloride. This carbon tetrachloride, as we shall continue to study chemistry in physical chemistry, they'll tell us that this carbon tetrachloride is an inert solvent. So being an inert solvent, it favors the splitting of this bromine molecule or bromine molecule into two ions, where it partially ionizes to form a partially positive bromide and a partially negative bromide. Then, as I told you, the one which will be having a partially positive charge, that is an electrophile. And we said that in alkenes, they have a pi bond added to them, and that pi bond acts as the center of high electron density. And then it will attack that partially positive bromide, and then the partially negative bromide, for that case to be highly electronegative, it takes that bonding electrons. Then you can continue and show the person uh, that you have lost that bromide, or in case you have failed to write it on top of the arrow, you can come back, you can come here on after the carbocation, then you write plus bromide ion. But if you just stop from here and then you don't identify this bromide, someone may stop marking from there. So you have to show that this bromide here is lost here, or if you don't write it on top of the arrow, you can continue and write it after you have written the carbocation. So now, when we form carbocation, this is a positive charged carbocation, and now this bromide ion, which is now negatively charged, will attack this is a tertiary carbocation, so it will attack this tertiary carbocation, and this bromide will also add itself to this carbon atom. Then another thing before I continue, or before I leave this slide, what you have to remember about alkenes, I know you covered this, the Markovnikov's rule and anti-Markovnikov's rule, whereby Markovnikov's rule says that the carbon atom near the double bond, the one with more hydrogen atoms, is the one which will first receive. So the first bromide will not go to this second carbon, but instead it will go to this the third or the first this first carbon to form CH2Br. Then we form a tertiary carbocation. Secondly, we shall find that formation of carbocations, the stability of those carbocations increase in the order of tertiary are highly stable, followed by secondary, then lastly followed by primary carbocations. So this carbon here holding the positive charge, you see it is not having any hydrogen, so this qualifies it to be a tertiary carbocation, which is highly stable. So it is the one that will be attacked. I'm sorry. It is the one that will be attacked by a bromide molecule or a bromide ion, and then we form that compound. Are we together up to that point?
Question.
Someone is asking that if I write the lost bromide both on the arrow And after, of course, when you write there you are on a safer side, because no one will penalize you that you have written it on the arrow, or you have written it on the other side. Someone is asking us to repeat for them. So let me repeat for the last time, and then we continue to the next mechanism. I've said that once you are again, okay. Something has happened, I don't know. Let me check. Let me share again. Okay, we are back. I had reached on. Someone was asking us to repeat for him or her, and I saw someone asking that is bromine aqueous equivalent to same as bromine stroke carbon tetrachloride. So you can write this equation as 2-methylpropene plus bromine aqueous. Then you put an arrow, and then you put carbon tetrachloride on top of the arrow. So they are the same, but not a gas. We are using bromine aqueous. Hopefully we are together. So this person who was asking us to repeat, I said that alkenes undergo electrophilic addition reactions, as we explained. And I said that in presence of carbon tetrachloride acts as an inert solvent, which allows or which favors the partial ionization of this bromine into a partially positive bromide ion and a partially negative bromide ion. So I said once the double bond attacking the bromide which is partially positive, the one which is partially negative, we lose it, or we can write it after the carbocation, and then we attack the carbocation using the bromide, which was partially negative, and then we form the final product. Hopefully we are together up to date. Then another day they may ask you, another day they may ask you to, because in UNEP this year they asked us to write that mechanism in presence of carbon tetrachloride, but they may ask us to do that mechanism in presence of water. So once we are given water, what can we do and what can the mechanism be? So in presence of water, we shall find we are forming we shall form 2-hydroxy, 2-methyl bromopropane instead of all the bromide ions attacking that compound, but instead now in presence of water, water will attack the carbocation, and the reason is that water is highly concentrated and has lone pairs which it can donate to a carbocation. So in presence of water, water is highly concentrated, so it will be the one to attack the carbocation instead of the bromide ion which was present when we had a carbon tetrachloride. So here the mechanism also starts in the same way, where bromine partially ionizes to a partially positive bromide ion and a partially negative bromide ion. Then the double bond on chlorine, which is here, this pi bond attacks the the electrophile, which is the partially positive bromide molecule. And the bromide ion, which is a negatively charged, takes up the electron because it is more electronegative, and then we lose that bromide, or we can write it the other side. But as I've said, in presence of water, instead of bromide ion attacking, water is the one which attacks, and it has lone pairs of electrons, which it can donate, looking for. And then finally, we shall form water attacking that carbon which is having a positive charge. But because oxygen accommodates only 2 bonds in any reaction, so when we add it to carbon, then it is having its 2 hydrogen, so it becomes unstable, and so you should remember to put a positive charge on that oxygen, showing that it is unstable. But some students, when they reach here, because they have seen it is unstable, they again lose water. But instead, we are supposed to lose a hydrogen, not to lose water again. Hopefully, we are together up to that level. Okay, we have another reaction, electrophilic substitution reactions. Which one in the zoo? You people, are we together? Let me ask. Someone can unmute. Whitney, you can unmute and tell me. Are we together?
We're together.
Okay. So we can continue. So we are going, I was explaining this reaction of electrophilic addition where I used what I think we all got what I was doing, though there was something with my phone that I was not understanding. Then we have another reaction, which is electrophilic substitution reaction. So electrophilic substitution reaction, as we hear, this is a reaction. This is a reaction in which the hydrogen atom in the benzene ring is replaced by an electron deficient species or is replaced by an electrophile. As I said, an electrophile, that is an electron deficient species. So as we know, I don't know if all of us or majority of us have studied benzene, but I think so. Benzene in its structure, it has each carbon atom in that structure is having hydrogen. And once we want to add any electrophile, the hydrogen atom is replaced, and then the electrophile substitutes where the hydrogen was, and we form other compounds. For example, we looked at reactions of benzene. We remember about reactions of benzene where we have alkylation of benzene. Alkylation of benzene, that is reaction between benzene and an alkyl halide. And this reaction occurs in presence of a halogen carrier catalyst. For example, aluminium chloride, iron 3, it was bromide, iron 3 bromide, among others. Then we also have acylation. Acylation, that is addition of acid halides to benzene ring. We have other reactions that benzene undergo, like sulfonation, where we react concentrated sulfuric acid under reflux, or where we react fuming sulfuric acid to benzene. So all reactions undergone by benzene, where we have that hydrogen in the benzene ring being substituted, that's substitution reaction. We also have, so I used that one which was asked in UNEP, where they asked us to describe the reaction between benzene with chloroethane. I don't know if the one, I think it's the one which was in UNEP. So as I said, if they say, describe the reaction, don't look at the word as maybe something strange or new, but you just, what you need, you identify which type of reaction is it, you identify which reagents are there, which conditions does this reaction need for it to occur, then name the major product. Majorly, you name the major product. So for this case, benzene with chloroethane, you would remember that this is an alkylation, which is an electrophilic substitution reaction, whereby you continue and maybe you can continue and say that the alkyl group from chloroethane substitutes hydrogen in the benzene ring. And this reaction occurs in presence of a halogen carrier catalyst. It may be iron, it may be, iron chloride, iron 3 chloride, or it may be aluminium chloride. So you identify that, then you outline that mechanism. So as I said, that reaction occurs in the presence of a halogen carrier catalyst. So we first break up the bond between an alkyl group and a halogen. And when we attack, okay, we add a chloride to aluminium chloride and we form, so where we shall remove that bond, it means this carbon which was bonded to chlorine, it will remain unstable because we expect that each carbon atom should be having 4 bonds along it for it to be stable. So once the reaction that we have taken one molecule from it, the carbon will remain unstable, and you have to identify it as a positively charged carbocation. Don't forget to put that positive charge because you show that it is electron seeking or it lacks an electron. So from there, the same way as alkenes and alkynes do, benzene itself has a mixture of double and single bonds. So the double bond in benzene can act as the center of high electron density and attacks or renders that electron towards an electrophile. So you see you can see the bond, this double bond attacking a carbocation, which is CH2CH3, and then because we say this is electrophilic substitution, where we have this hydrogen being removed or being substituted. So we expose this hydrogen molecule because we are replacing it with an ethyl group. So when we remove the bond, the double bond which was in benzene ring, then this bond remains, or this molecule remains, it remains unstable, and you have to indicate that instability by indicating a positive charge, as you can see that I have put in my ring. Then this hydrogen, the bond which is bonding hydrogen and carbon, neutralizes this positive to bring back the double bond in the ring, and then of course we lose that hydrogen. As you can see, I have lost that hydrogen, and finally I form phenyl ethane as the final product. Are we together? Actually, why benzene undergoes electrophilic substitution reaction? So someone is asking that why does benzene undergo electrophilic substitution reaction? So as I said, benzene has a mixture of double bond and single bonds, and of which they keep alternating. So it can render its double bond towards electrophiles. It can render its double bond towards electrophiles. But remember, we have said we have a single and double bond. So where the electrophile has attached, that carbon remains unstable, being that benzene being in a ring. The carbon now will, if we remain with hydrogen, that carbon will be having 5 bonds. So one bond, that hydrogen must be lost so that we remain with that carbon where the electrophile has substituted to form a stable structure. Are we together? Okay, so we can continue. Okay, someone is asking us to explain the description of the reaction. I said the reaction that benzene undergoes is electrophilic substitution reaction in which the hydrogen atom in the benzene ring is substituted by electrophiles. Benzene, just like other alkenes or other unsaturated compound, it is also unsaturated, but for it the difference is that it has a mixture of both single and double bonds. So the double bonds and single bonds keep rotating with each other. So once we attack, for alkenes we attack, and because it is a linear structure, we don't need to lose the hydrogen because the carbon remains stable. But for this case, the single bonds and double bonds are rotating with each other. So once we bring in another molecule, the carbon on which we have brought that carbocation, I mean that electrophile, it will remain unstable. So we have to lose that hydrogen, hence making the reaction substitution reaction. Then we can go to another type of reaction, which is nucleophilic addition reaction. Nucleophilic addition reaction, as you hear the word nucleophilic and addition reaction, these are reactions where where a nucleophile is being added to unsaturated organic compound to form a saturated organic compound. And this reaction, it is only and majorly undergone by carbonyl compounds. I don't know if we have reached up to carbonyl compounds, but the carbonyl compounds, that is aldehydes and ketones, undergo this type of reaction, and we shall give a reason why they undergo this type of reaction. So by definition, this is a reaction in which an electron-rich species adds itself across the unsaturated bond to form a single product with no loss of any atom, and the nucleophile acts as a source of electrons. So let me, okay, I will allow you, Precious, very soon. Let me explain this type of reaction based on its mechanism. Okay. Precious, you can first unmute and ask.
I was asking about that question where you talked about when the examiner asks you describe the reaction, where you talked about answering in a form of mentioning the type of reaction, then indicating the condition, something of that sort. That's what I wanted to inquire about.
Oh, okay, I forgot what you're asking. So, for example, assume this reaction that I'm having here. This is propanone reacting with sodium hydrogen sulfide. So assume the examiner has asked you to describe the reaction between propanone and sodium hydrogen sulfide. So by this, you first identify which reaction do these molecules, do these compounds undergo. So for example, the reaction between propanone and sodium hydrogen sulfide, this is a nucleophilic addition reaction. So you will say propanone and sodium hydrogen sulfide undergoes nucleophilic addition reaction, whereby now you talk about how does this reaction occur. So whereby hydrogen sulfide from sodium hydrogen sulfide is added to the carbonyl compound or to the carbonyl carbon in propanone to form this compound here, which is 2-hydroxypropane sodium sulfide. So you continue to talk about the name of the major product. We don't talk about the intermediates. You talk about the major product. You name the type of reaction. You talk about briefly how that reaction occur. Then if there is a condition allowing that reaction to occur, you further tell us that this reaction is favored by this. For example, if it is maybe carbon tetrachloride as we looked at before, or if it is in presence of water, or if it is in presence of dry ether, whatever reaction, then you continue to name the product which is formed, and then you outline the mechanism. Hopefully you have understood what I have answered you. Okay, someone is asking me to pardon. I've said if you are given a reaction, let me go back briefly. I want to use this one, which is having a condition. For example, this reaction here, which is benzene with chloroethane, and we see it cannot occur freely. So there is a condition in which this reaction occurs. So you will say benzene and chloroethane undergoes electrophilic substitution reaction. So that is the type of reaction. Then you briefly say where an alkyl group from chloroethane attacks or is substituted with hydrogen from benzene ring. And then you can continue and say this reaction occurs in presence of aluminium chloride as a halogen carrier catalyst, leading to formation of this compound, which is phenylethane. You have described the type of reaction. You have talked about briefly how that reaction occurs. Then you have continued to tell the person the condition in which this reaction occurs, and then the product, which is phenylethane. Then from there, you outline the mechanism as they will be asking you. Hopefully you have now understood. So, as I was saying that nucleophilic addition reactions, this is a reaction in which an electron-rich species adds itself across the unsaturated bond to form a single product with no loss of any atom. And here, the nucleophile acts as a source of electron. This reaction is undergone majorly by carbonyl compounds, of which carbonyl compounds we have aldehydes and ketones. And we have major two reactions, nucleophilic addition reactions in carbonyl compounds, where we have a reaction between carbonyl compounds and hydrogen cyanide, and a reaction between carbonyl compounds and sodium hydrogen sulfide. So for this case, I used sodium hydrogen sulfide as one of the electron species that I use. So I used the propanone, which is a ketone. If you have not looked at them, you will look at them as we start the first term. For those who have looked at them well, so this propanone here, as you can look at this compound before, let me see. This molecule here, it has a carbon, or the carbonyl carbon is the one which is bonded to oxygen in that compound. So this carbonyl compound, this carbonyl carbon and oxygen, as I can say, oxygen is highly electronegative compared to carbon. What do I mean by being highly electronegative? it means it can easily take up bonding electrons towards itself. It has the ability to attract electrons towards itself compared to carbon. So oxygen here is highly electronegative, and being highly electronegative, it can pull the bonding electrons towards itself, and once it takes the bonding electrons towards itself, it forms a partially negative charge on itself, and it leaves a partially positive charge on the carbonyl carbon. So once it leaves a partially positive charge on the carbonyl carbon, it makes it susceptible, or it makes it favorable, or it makes it sufficient to be attacked by nucleophiles. So for this case, our nucleophile is hydrogen sulfide, which is from the reaction between, the ionization of sodium hydrogen sulfide. Sodium hydrogen sulfide ionizes to give us sodium ion and to give us hydrogen sulfide ion. So hydrogen sulfide, for this case, it is having excess electrons, or it is an electron-rich species. So it will attack the carbonyl carbon, because as I've said that oxygen pulls up the bonding electrons towards itself, creating a partial negative charge on itself, leaving a partial positive charge on the carbonyl carbon. So the carbonyl carbon now remaining positive, it can easily be attacked by a nucleophile. So I wrote this hydrogen sulfide in its structure, its bonding structure, whereby sulfur is bonded to, is supposed to be bonded by 6 bonds, but it uses only 4 out of the 6 outermost electrons, leaving a lone pair of electrons on sulfur. So this lone pair of electrons, it can donate to this carbonyl carbon. And then once you are doing a mechanism, you make sure that the arrow is between the 2 dots, or the 2 lone pairs of electrons. And of course, for any reaction, once we are talking about carbon, we should make sure that this carbon is having 4 bonds attached to it. This carbon should be having 4 bonds attached to it, and therefore, once we bring this arrow showing that we are reacting this hydrogen sulfide with this carbon, it means that carbon will acquire 5 bonds. And we said carbon should be bonded to only 4 bonds. So it becomes unstable. And of course, this double bond has to break off. And then it creates a negative charge on oxygen. As you can see from here, you can see this now oxygen acquiring a negative charge, and then this molecule here, which was this one, the hydrogen sulfide, also attacks itself on carbon. Then we shift the hydrogen, this hydrogen which is on the, where have I tapped? Okay, I'm saying which hydrogen, this hydrogen which is on the hydrogen sulfide, we shift it to this oxygen, so that we form a hydroxyl group, and then we shall create a positive charge, or I mean a negative charge on this sulfide. And then equations which are partial, or which are reversible, where we have reversible arrows. Once you are doing a mechanism, you should be serious with them, because you can easily lose that mark when you have a right thing. So if you write your arrow, if you make your arrow, the arrow which moves where you are going, it is where you should write that word. So if you are writing proton shift or hydrogen ion shift, you should write it on the half arrow, or on the single arrow which is going where you are going. Don't come and bring this hydrogen shift and you write it this side. It means that you are writing the mechanism upwards, and of course it will lose meaning. So you make sure you write that word where you are going, where the mechanism is going. Don't write it anywhere, or don't just write for the sake. Make sure you write when you want marks. Otherwise, you lose marks. You come out of the paper telling people that, oh, you know what? All the numbers of organic have got 20, when in actual sense you have got like 10, just because of simple mistakes that you have made. So once we shift this hydrogen to this oxygen, we form an OH here. And I think I lost my, yes, it's okay. So once we shift this hydrogen, we create a negative charge, and now sodium can go freely on that negative charge to neutralize it, and we form this compound. This positive charge is not there. I think it was a mistake when I was writing. And once you put it the way I have written, then you make sure that even on sulfur you put a negative charge, but you don't leave it the way I left it. I think I just made a mistake when I was writing. I see people, are we together? How do you know it is reversible? So someone is asking us that how do we know that it is reversible? I don't know if I have the exact answer, but most of the reactions where we have shift, where we are shifting hydrogen, where we are shifting a methyl, those reactions are reversible. It can go back to the reaction where it is. Okay, it can go back to the backward reaction. So I think you will get it that when we are shifting when you are shifting a hydrogen, or you are shifting a methyl, then that reaction is reversible, because this hydrogen can go back to its original position, and we again go back to this step where we are. So the reaction is reversible. Any other question? I see someone is asking, where is the mistake? Oh, the mistake I was talking about, I say, do you look at this sodium, the final product here which I have? I wrote sodium positive, like I brought a positive charge on this one. I said this is a mistake. You should not write this, because like if you want to write a positive charge on sodium, you continue ahead to write a negative charge on sulfite, so that they neutralize and the compound remains stable. But when you put only one charge, like a negative charge on sulfite or a positive charge on sodium, then it shows that the reaction is unstable. So you should make sure that the compound that you have ended up with is a stable compound. One day they may ask you to write like for example in paper 1, they may say complete the mechanism. Complete the reaction, naming the major products, and sometimes they go ahead and ask you to write the observation. So the observation for this compound, this final product here, is practically seen as a white precipitate. So one day if they ask you to explain the to write the major product, and then you write the observation, remember that they form a white precipitate. Or maybe if you are doing, sometimes you'll be doing an empirical formula, like these questions of empirical formula, where you have to first calculate the empirical formula, then you get the compound. They may tell you to that substance or compound Y reacted with sodium hydrogen sulfide to form a white precipitate. They may give you that information. So you should be having information in mind that carbonyl compounds, when they react with sodium hydrogen sulfide, they come up with a white precipitate. Or even for any other reaction, sometimes they trick you. They say maybe compound Z decolorizes bromine water, or it, like they tell you the observation, so that if you have the knowledge of the compound, then you'll be able to identify the isomers of that possible compound once you have read through the equation, I mean the question that has been given unto you. Can I have your contact info? I really need your help. I will send it before we finish. Okay, we can continue to the next reaction, which is nucleophilic substitution. Let us first leave the word unimolecular, and we have nucleophilic substitution reaction. A nucleophilic substitution reaction, just as we looked at electrophilic substitution reaction, nucleophilic substitution reaction, here we are substituting a nucleophile. The other side, we are substituting hydrogen in the benzene ring. But for this case, we have a nucleophile in the compound already, but then we want to replace it with another nucleophile. And this reaction here, and it is in two categories or two forms or two types, where we have unimolecular reaction and the nucleophilic substitution by molecular reaction. So for nucleophilic substitution unimolecular, that is the reaction. That is the reaction where the hydrogen atom or any other, the hydrogen atom in a tertiary alkyl halide is replaced by a nucleophile. This reaction, the nucleophilic substitution unimolecular, is the same as SN1. So this is the reaction where we have majors, or specifically, we have one intermediate or one species in the rate determining step. The rate determining step, that is the main step, the main step in a chemical reaction. So we shall find out that in the rate determining step, we only have one species, and for this case, this reaction is undergone by tertiary alkyl halides. Tertiary alkyl halides, those are alkyl halides in which the carbon bearing the hydrogen, is not having any hydrogen. So it is having all the three alkyl groups, and there is no hydrogen on that carbon. So that's the tertiary that's the tertiary alkyl halide. Then so we say it undergoes nucleophilic substitution in molecular because the tertiary alkyl halide can easily dissociate or can easily give out the hydrogen, creating a tertiary carbocation which is highly stable, and that tertiary carbocation can easily be attacked by nucleophiles, and so that will be a nucleophilic substitution unimolecular reaction. This reaction is majorly undergone by tertiary alkyl halides, but for in any case they give you a secondary alkyl halide. The secondary alkyl halide can also undergo that type of reaction, but the secondary alkyl halides, for them they predominate. SN to the nucleophilic substitution by molecular. So for tertiary, for them they are majorly they undergo unimolecular. Then we shall find out that nucleophilic substitution by molecular reaction, we shall find that for secondary alkyl halides, for them they undergo both, but majorly they undergo the nucleophilic substitution by the reaction. So for example, they may give you a reaction between any tertiary alkyl halide and sodium hydroxide. So it may be sodium hydroxide, it may be potassium hydroxide, as long as it will give us a nucleophile which is an electron-rich species. whenever we are given. It may be an amine, because we shall find out in the future that ammonia or nitrogen in any reaction, also like oxygen, it has lone pairs of electrons, which it can easily donate it to electrophiles and attack them. Someone is, what if I present compound by two half arrows? Right? Ionization of compounds. We use double arrows or reversible arrows for weak electrolytes, like sulfuric acid, like other reactions that do split. We have nitric acid, they undergo reversible arrows or half double arrows. But for sodium hydrogen sulfide, it is a strong electrolyte, so it dissociates or ionizes completely. Is little wakati atanigejaji network. So kinda
Yes. May I ask Sophie? Nabukenya Sophie? 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 Oh, teacher parent, can you be able to unmute now? Sophie? Sophia?
Yes, sir.
Yes. Kindly give me the host rights. Click on my name and say make host.
Yes, sir.
Click on my name and say make host. Click on my name.
Okay. So is it fine right now? Hello.
Yes, let me check. Yeah, it is okay. But I'm trying to get the teacher. Allow me to
Okay.
first get the teacher back.
Okay, sir.
Okay, thank you. Friends, network here disturbed me a bit and I switched off. But hopefully we are back now. So we had reached as far as I was talking about electrophilic, nucleophilic substitution. In molecular first share my internet. So as I told you, that is a reaction in which the hydrogen atom in a tertiary alkyl halide is replaced by a nucleophile. And I said it is majorly the tertiary alkyl halides which can easily break
Hello. Madam, aren't getting.
The members. Thank you for being patient. 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 So, 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 we were talking about nucleophilic substitution in molecular. Let us continue rewind up. So I say that the nucleophilic substitution in molecular, that is a reaction where we have two species, I mean one species in the rate determining step. So for example, a reaction between this alkyl halide, I have this alkyl halide, which is two, two methyl, two chloro, from butyl, reacting with sodium hydroxide aqueous under heating, we shall form, I made a mistake. This chloride was supposed to be, this was supposed to be a hydroxyl group. As you can see in the final, disappear. How you people, you will forgive me, I don't know. The computer has refused my network here. So I'm finding it hard. Okay, let's continue and finish and wind up. So I said it is a substitution. So this hydroxyl group from sodium hydroxide will attack the carbocation that we have formed, and it substitute where there was a chloride, there will be substituted a hydroxyl group, and then we form this tertiary alkyl from a tertiary alkyl halide. We also have a secondary alcohol can also undergo the same mechanism, or can undergo the same reaction, just like tertiary alcohols, tertiary alkyl halides. However, I said that for secondary alcohols, they undergo both, but preferably it is the bimolecular reaction which is undergone by secondary alkyl halides. But in case you can also write this one. For example, this question came in UNEB and they wanted us to talk about the reaction, to describe the reaction between 2-chloropropane and sodium hydroxide. As I started telling you, once they tell us to describe a reaction, first of all, we identify which type of reaction does this compound undergo. So for this case, you would either use a unimolecular reaction or a bimolecular reaction. So you would say 2-chloropropane react with sodium hydroxide. Before you write that, you say the reaction between 2-chloropropane and sodium hydroxide solution is a nucleophilic substitution unimolecular reaction. Then you would say that the secondary alkyl halide dissociates or ionizes to liberate chloride ions and forming a secondary carbocation, which is attacked by hydroxyl group from sodium hydroxide, forming this is propan 2-ol. Then you outline the mechanism. I said you talk about the type of reaction. You briefly describe the reaction, identifying any condition given. For example, this reaction occurs on heating. The condition for this reaction to proceed is heating, and of course, we have sodium hydroxide dissociating. Sodium hydroxide is a strong electrolyte. I don't expect you to write a two-half equation. I mean 2 half arrows, because this is a strong electrolyte. It completely ionizes to give us sodium hydroxide and hydroxyl ions. So this reaction where we have the chloride dissociating or this bond breaking, it is a slow reaction. So when you are writing a mechanism, sometimes it is okay when you write the word slow on these two arrows, showing that the equation or the reaction is a slow, though it occurs, but it is slow. And then finally, we have the first step, where we have the hydroxyl attacking the carbocation and we form the alcohol, for this case, which is propan 2 or a secondary alcohol. Then bimolecular, that is a reaction in which in the rate determining species, in the rate determining step, we have two species. We have two species involved in the rate determining step, where we shall find that the alkyl group is partial, or the halide in the alkyl halide is partially breaking, and then we have the nucleophile bond partially forming onto the new compound that will be formed. So that's why we shall call it a nucleophilic substitution bimolecular. The reason is the halogen bond, the carbon halogen bond in the alkyl halide partially breaks, while the nucleophile carbon bond is partially forming in the rate determining step, and we will find out that the order of reaction for that is 2, as we shall study in physical chemistry in chemical kinetics. So we shall find out rates of reaction and orders. So this reaction measure is undergone by primary alkyl halides, as I said before. However, I told you that secondary alcohols, they go wherever you put them, is where they can go. So they can undergo this type of reaction efficiently compared to SN1. I again used the same example, which was in UNEP last year, where we have, for this case, we have the hydroxyl group from sodium hydroxide attacking the carbonyl, or this carbon. It's a slip of the tongue to talk about the carbonyl, but it's a carbon, the carbocation, which is partially positive, because remember, this halogen, this chloride, is highly electronegative. So it has the ability to put bonding electrons towards itself, leaving a partial positive charge on this carbon atom, creating a partial negative charge on the chloride. So once this OH, the bond can attack the carbon while we have this breaking, but we shall find out that it does not break completely, as we can see in the, those who are writing on the, those who are writing on the screen, please. So let me go back. I have a mechanism. You see this complex here that I put in the bracket. What's wrong with mine? So this compound that I put in the bracket, that is the species in the rate determining step, whereby we have chloride partially breaking, and then we have hydroxyl group partially forming, and then now we shall have it breaking completely. I forgot to put an arrow on this chloride here. Let me try to make it somehow. This here, we are supposed to put an arrow here showing how today we lose it, and we form an alcohol, as you can see. Then you can continue and terminate the mechanism by getting this sodium here plus the chloride, which was lost, and then you form sodium chloride as you are terminating the mechanism. So that is about nucleophilic substitution. Those questions you can put in the chat room, and I can answer to them. Then we have, I think this is the last equation, the last reaction, elimination reactions, as this is a reaction in which a nucleophile eliminates an atom or group of atoms to form unsaturated compounds. So here we shall find out that saturated compounds, but with, some atoms will be lost, and then we form unsaturated compounds. For example, this reaction also is in two forms: elimination unimolecular and elimination bimolecular, but I didn't specify them, but it is in EN1 and EN2. Elimination unimolecular and elimination bimolecular, where unimolecular you lose only one species or one atom or one group. Then in bimolecular you lose two. So for example, we have dehydration of alcohols. This is a common reaction that the majority of us are conversant with. Formation of alkenes from alcohols, and here you should specify the temperature, as we shall look at some reactions of alcohols with concentrated sulfuric acid at different temperature. They bring different compounds. So once you are outlining a specific mechanism for this reaction, you specify a temperature of either 170 degrees Celsius or 180 degrees Celsius. You have to be specific so that you form an alkene, not any other compound. Then we also have reaction of alkyl halides with hot alcoholic potassium hydroxide to yield alkenes and alkyl halides to form alkynes. When you have alkyl halides and you react with potassium hydroxide in presence of ethanol on heating, then you are likely to form alkenes if it is a secondary and a tertiary alkyl halides. I believe majority of us were told that primary alkyl halides, for them, when you react with hot alcoholic potassium hydroxide, they yield ethers, not alkenes. So when you will be doing synthesis, please don't make that mistake and have like you have chloroethane, then you put this reaction to say that you are forming an alkene. That one will be wrong. For primary alkyl halides, once they react with this reagent, they liberate ethers, not alkenes. You should get it from today so that in any case you are doing any synthesis or you are doing a mechanism, specifically a synthesis, you don't make a mistake and you write that reaction there. Then if it is having two halogens or if it is a dihalide, we are likely to form an alkyne, as we looked at alkynes. If you looked at reactions of alkyne or formation methods of preparation of alkynes, there is why we have that reaction. I happen to use, so this is for elimination. The first elimination, the molecular. Here I used the simplest alcohol. Enable may not bring ethanol. It may bring a ring, maybe it brings phenyl ethanol, or it brings something, but having a hydroxyl group. You should not lose a track by the compound actually. You may calculate, for example, during MOX, you will be you calculate an empirical formula, then a molecular formula, but you realize that the compound which comes out is maybe a bigger compound. Don't worry about the compound. What is to be worried about is you just mind about the functional group. If the functional group is an alcohol and you have studied alcohols, follow the same trend and follow the same techniques, the mechanisms that are undergone by alcohols, then you write that mechanism. You shouldn't fail to write that mechanism because they have maybe complexed the organic compound. Just mind about the functional group. So for this case, I used the simplest alcohol, ethanol, whereby alcohols, they have OH or hydroxyl group in their structure, and that oxygen which is in that structure, as I told you, it has lone pairs of electrons, because we know that the outer electronic configuration of oxygen, it has 6 valence electrons in the outermost shell, but then it uses only 2 for bonding, meaning the other 4 remain as 2 lone pairs of electrons. So whenever it is in a reaction, it can easily donate those electrons towards electrophiles or towards positively charged ions. So the lone pairs of electrons from oxygen will attack the hydrogen ion. Will attack the hydrogen ion, as you can see, and then we form OH2. I told you oxygen in bonding, it only uses 2 electrons. So once they become 3, it is unstable, and then you should show us the instability of oxygen by putting a positive sign, showing that it is electron deficient or it is unstable. Then from here we lose water. That is water. OH2 is water. We lose it and we form a carbocation. So for this case, we had split sulfuric acid into hydrogen and hydrogen sulfate. And this hydrogen sulfate, as you can see, it has a negative charge, or it is electron rich. So it can donate its electrons towards the carbocation, and it takes this hydrogen. And once it takes the hydrogen, that bond between hydrogen and carbon it forms a double bond, and finally we end up with an alkene. Lydia, you can unmute and ask. Unmute.
Madam, are you hearing me?
Yeah, I'm hearing.
I thought that the hydrogen ion, the hydrogen ion is the one attacking the OH, not the lone pairs to attack the hydrogen ion.
So, okay. Thank you for that question. You can unmute. So when you see this hydrogen with a positive charge, it shows that it is electron deficient. Are you hearing me? So it is electron deficient, so it cannot attack, but rather it is attacked. So oxygen here, this oxygen which is having excess of electrons, hope it is clear with you. Let me hope that it is clear now. It is the one which is attacked. I mean, the one which attacks is the one which is electron rich. Then the one which is electron deficient, it is attacked. So for this case, hydrogen having a positive charge, it shows us that it is electron deficient. So it is looking for electrons. But oxygen itself has extra electrons, the unpaired electrons, which are lone pairs. So these lone pairs, it can donate it to hydrogen, and the reaction continues. I see people the one of Infinix Smart or Smart, you can unmute. It's not allowed.
Excuse me, madam.
Yes, you're excused.
Yes. My name is Rachel. I want to ask you, is it okay when you don't show how the water is breaking off from the compound?
Oh, I get you. Here when I was typing, I think I made a mistake, but I was supposed to show an arrow here. I mean a bond between oxygen and carbon. Then I break it out as I lose this water. Thank you for that submission.
Thank you, madam. You're welcome.
Okay. Then this is for bimolecular, where we have to lose more than one species or one group of atom. For this case, in this reaction, this is for dihalides, and this reaction is in methods of preparation of alkynes, where we have alcoholic potassium hydroxide. For this case, they had already formed as our ethoxide, but in case they put ethanol and potassium hydroxide, you get potassium hydroxide first, you react it with ethanol, so that the ethoxide ion will be having a negative charge, or it will be having an extra electron, and then you donate it to this hydrogen. So the reaction, we attack hydrogen, then the bond between carbon and hydrogen is formed. It forms a double bond here. Then you break off the bromide from the next carbon, not the same carbon you have attacked. Many students, when they reach here, they make this mistake, and you find someone is losing this hydrogen at the same time losing this bromide. That will be not clear, because this carbon here, I told you it should be having 4 bonds, meaning if you lose hydrogen at the same time you lose this bromide, then you are making this carbon unstable. So we lose carbon from the next, we lose bromide or chloride or any other halogen from the next carbon, not the same carbon we removed the hydrogen. Then we have, the reaction continues, we lose another hydrogen as we create a triple bond. Then now finally we can lose that bromide. Then another thing which misses in this mechanism, you can show here on this arrow minus Br. Where that Br went, you can put minus Br minus, even here minus Br, and then finally you end the mechanism. I think those are the major reactions that we have. And then someone may ask you such a question, or another person may ask you the question we have finished. If you check in UNEB past papers, you'll find out that these questions are always there. When you reach in senior 6, majority of us, you tend to ignore these questions. You say, these are form 5 questions. But UNEB will surprise you and will ask you such a question, and it says, write short notes. So someone, when they reach in senior 6, they say, those questions are for senior 5. And you find you are ignoring those questions, but should always take time when you are reading. Make sure you read through each and every equation, because it is through mechanisms. If a student knows mechanisms, then it is obvious synthesis will be simple for you, because mechanisms, when you are writing a mechanism, you are writing even the condition, you are writing the steps that occur. So meaning, if someone asks you to write the synthesis of a certain organic compound from the next, you can link up all the knowledge of mechanisms. So it is mechanisms that you can understand, that will help you to write all the synthesis that you will be requested. So one day they may ask you such a question where they want you to write short notes, and force you write a relevant mechanism. Majority of them, we did them. The hydration, we did it when I talked about elimination reaction. Friedel-Crafts alkylation, I had that question, benzene with alkyl halides. Then this one is the hydration, that is eliminating water from organic compounds, like for example, reaction of alcohols with sulfuric acid at 180 specifically, or 170. That one is an adhydration reaction. Then Friedel-Crafts alkylation or acylation. They may use a term that may be new to you, but this one is acylation, where we are adding acid halides to benzene. So you should not get confused along the way. Lastly, we have esterification. Esterification, we shall find out when we deal with alcohols and carboxylic acids, as this is the reaction between alcohols and carboxylic acids, and then we shall outline a mechanism later. I think for today, we shall end up from here. Thank you guys for being patient, because network disturbed us a bit, but I thank you for you became patient until we reached the end. Next time we shall deal with synthesis, how we can synthesize various organic compounds from other organic compounds. Lydia, let me unmute you. Lydia.
Sorry, madam, it's a mistake.
Okay, it's fine. So we can stop there. Thank you for you have given me your time, and thank you for you have made the discussion lively because you interacted with me. I thank you so much, and I continue to wish you success from today, because success starts from today until you will receive the results 2026. So I wish you nice preparations, and We meet next time. Thank you.